All right. Let's do a little cross-curricular action here. Yeah, let's talk about math and chemistry. So when you have a chemical compound, okay, that degrades naturally, right? Like sometimes that we might be talking about biodegradable compounds. Sometimes we might be talking about radioactive isotopes. Okay, it's a popular question that we have here in this unit. We talk about this term called half-life. Okay, now half-life, one cheap definition. This is one that I wrote, is the amount of time it takes for a sample of an element or compound to decrease by 50% of its original mass. So here's an example. Here's an illustration of what we're talking about with half-life, right? Suppose you start with this initial amount. After one half-life, right? So this is a unit of time that we call a half-life. After that period of time, half of what you started with remains, right? And after another full half-life period, you have half of what that amount was. And then you have half of what that amount was. And then you have half of what that amount was. So you see it go from 10 to 50 to 25 to approximately 12, but really what? 12.5% to 6.25 to 3.0625, yada, 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 right? So when we talk about half-life, this is an example of an exponential decay model, okay? Because the amount that it's going down by isn't the same, right? But the percentage that is going away is the same, right? And percentages are a multiplicative operation, right? So when you see this, we lost half, but to go from half to a quarter, we only lost this much, right? And to go from a quarter to 1/12, we lost this much. So we're not losing the same amount every half-life period. We're taking half, okay? So a different illustration of that would look like this. So you can see here on the y-axis, percentage of original isotope remaining. This is radioactivity, okay? So after 0 half-lives, you have 100% of this isotope, whatever it is, 100 grams, 500 grams, 1,000,000 grams, whatever that number is, you have 50% of that after 1 half-life. After 2 half-lives, you can see where this is, right? My drawing is not perfect, but you're going to have 25% left. So half-life is an amount of time it takes to lose 50% of some amount that you started with. So here's an example of a half-life question. We're going to use this, and sorry, but not to go too fast here, but this is an exponential decay model. It's clearly not linear, right? We're multiplying by half every time to decrease this number over and over and over again, right? But what we do to generalize this is we use, okay, our exponential decay model to express half-life, which is, again, explained in a previous video, where we have A naught, right, the original amount or some amount, and then this decay happens. That's the rate of decay for a certain period of time. E is E, right, not a variable. And then we have the value that's left after some period of time, okay? So since we don't always start with the same amount, we use that half-life model like so. This is our exponential growth / decay model, right? When we're talking about half-life, we're talking about decay. Right? Let's be clear about that. So this question asks, at what rate? Okay, so first, before we even read the entire problem, at what rate, right? We stopped using R and we started using K. So this is the variable that we are solving for, okay? At what rate is a radioactive material decaying if after 150 years, 100 grams remain of a 200-gram sample, okay? So the idea of this is a half-life, right? If we start with 200 and we end with 100, okay? So we know that the half-life is 150 years for this radioactive material, okay? Half-life and decay rate, okay? These are connected, right? These are not, I realize that they're variables in the formula, but these are not variables in the sense where they can change. If the half-life of this is 150 years, then its decay rate is going to match that, right? It's going to be tied to that idea. It's not 150, okay? but whatever the decay rate is for this will always be the decay rate because the half-life isn't going to change for this material. So if we have a 200 gram sample at the beginning, that's our A naught, our original amount. There's 100 grams left of this after 150 years. Okay, so we have another exponential equation. And we've talked about solving this by isolating the power, right? Getting the entire exponential term by itself. So we would have to get rid of the 200. So we're dividing by 200 here. And we're dividing by 200 here. And that gives us, let's call this 1/2 or 0.5, whatever you want. This is e to the 150k. Okay. Now, when we solve for a variable that's in the exponential level and our base is e, to knock this down onto the base level, we have to log both sides, and we're going to do natural log. We're using natural log because, once again, natural log is log base e, right? And we want log base e of e because that's going to simplify that whole term, right, when we get there. We'll talk about that when we get there. So we have the natural log of 1/2 is equal to 150k, the whole variable, the whole exponent in the variable comes down, and we have the natural log of e, and the natural log of e is log base e of e, which is a number. It's the number that I put as an exponent to this to get this, right, which is 1. So this natural log of e has a value of 1, which gets multiplied times the 150k, excuse me, and then we divide by 150 to solve for k. Okay, so we get k is approximately whatever the natural log of 1/2 divided by 150 is. Lucky for you, I've got my Desmos ready to rock, which is negative 0.00462. So we'll go with that. Negative 0.00462. Okay, and this is a percentage, right? So it's really negative 0.46%, right? As a rate, as a value, it's this. As a percentage, it's this, right? When we move that decimal 2 spots, you're going to see a negative number here when this is decay, okay? And the reason for that is because what do negative exponents do, right? They push those values, they push those exponential values into a fraction. This base is greater than 1. So to think about why this decay rate is negative, this base is greater than 1, right? If I multiply 200 by a number that's greater than 1, that's going to exhibit growth, right? But we're decaying, which is exhibiting, not the opposite of growth, right? So we need to shove this entire power underneath this number to divide it to make it smaller. Okay, that's why that k value has to be negative in our half-life problem.